Hello, everyone. Welcome again after our lunch break. Now, our next session will begin by Mda Güleşen. She will show you how to analyze Mda simulation data. Sevilay, stage is yours. We can't hear you right now.
Thank you so much. So let me a minute. Yes, not this one, not this one. Okay. So welcome to everyone. Today I will try to explain how can we analyze our MD analysis, analyze our MD data. You'll learn how to do MD simulation up to now, and now we will try to analyze by using this MD data with VMD. Then I will try to show how can you analyze this MD data by using the R program, RStudio. Then I will briefly explain the MD analysis tool, which is the Python program, a Python tool for the Python programming languages. And I try to show 3 different ways to do this analysis. I hope it will be enough, I think, for you. And now let's start. Firstly, I would like to show to you this output data, which was explained by the Burak in the previous session. After the MD simulation, you will get actually normally these datas. This is very huge. And to analyze it, actually, we need only 3 of them. You can find if you do this MD simulation on your computer, you will get this a lot of data. But to do this analysis, you will just need the PDV or PSF and also DCD files. And also you can check your output file, log file, to check the MD simulation adventure, let's say. How can it run actually? Then conversion from different software to DCD probably. Actually, I'm not sure I can do it, but I will explain the each question later. So firstly, you will need this equalization out file. Then you will need this production out file. Firstly, in the MD simulation, you will do the equalization. Then you are you stabilize your system, then you are doing the production, and to do analyze it, you have to combine these 2 DCD and these 2 output. So I extract this one, you can find from the MD file, and I extract these files that we need actually to analyze it. So firstly, I will compare these out files for the with ligand. And to do that, I would like to open it with the terminal, because the actually file is very huge. And when you try to open it with the text file, sometimes the text app can be crash. That's why I would like to use this terminal. So let me see where we are in here. Then I'm going to with ligand part. This is our first case, and in here you can see out files in here. So firstly, I am checking the step 4 duration out. Then you will see this one. So in here you can see this is the output file, and you can actually get information about the simulation run from this file, you can find the time step in here, and also you can find these cell bases that these 77 means are frame number. And in here, where is it? And in here, these frequencies in here, that means you will write your energy function, your actually record your energy at each 5,000 step. This is the explanation of this 5,000. And you can see these are the input file, I think. Yeah, and these are the, pardon, sorry. These are the output file, which is DCD. And this is the file name, Calculation. And what else? It is very huge file, by the way, and complicated. So when you go down, you will see the structure summary and summary of parameters in here. You will see the bond number, angle number, dihedral, improper, cross term, van der Waals pairs, etc. in here as a number. And you can see time for reading PDB file. And also you can see structure summary in here. That means actually contains every atom inside the system. Then what else? In here, you will see your energy starting from the 0, then continue with 1, 2, 3, 4, 5, and it will continue to the end. That means 135,000, and this is your end step. And you will see the CPU time in here, memory in here, wall clock in here, and this energy calculation will be done for each energy step. And you can see the information about the time step in here. This is the time step, bond potential represented in here, angle total, dihedral temperature average, improper pressure, electrostatic G pressure, van der Waals volume, and boundary pressure average, etc. These are the summary for each step, and this is the minimization step, because we are trying to minimize. We are trying to stabilize our system in this step. So let's check the production step out. Yes, in here. You can see there are 2,500,000 number of steps. And so then what else? DCD frequency is the same, not the same, sorry, 50,000 in here. And what else? In here, you will see each energy steps actually is written every 5,000 step. Okay, this is the actually for the production phase. The energy is recorded each 5,000 step for the production part, and it will continue to the 2,500,000. And you can see again the bond potential, angle total for this energy step, and dihedral temperature average, improper pressure, etc. And you can see the CPU time in here, memory is which is used, and wall clock in here. You can check the condition from the out, condition of the run from the out file. So let's start to do. And if you want, we can check the also without one, without ligand, change directory, without points, and yes, let's step 5, for example, let's test this one. And when I go down, you will see this CP time will be different from the first one because the systems are different, but the main parameters are the same. And that's why you will see 2,500,000 energy time step in here. So that's it for the out file, log file. So I am continue with the VMD. Now I am opening the VMD. Yes. It is not working. Why? Let's check it. Yes. So now first we will open our PDB file. Firstly, I will start with the without ligand structure, which is the in here and files to be used. So firstly, without ligands. Now I am uploading the step 3 input PDB file. The PDB file will be the same for each step, and for the accumulation or production, the PDB file will be the same. That's why we can open one of them. So then this is our PDB file, and you can see the water in here, water box, and you can see the frame number in here. In the PDB file, normally we have one frame. Then I am adding the accumulation. It is 28 frame and production. We have to open each Dcd file onto step 3 input PDB file, because they are the same system. That's why we have to combine each Dcd file and PDB together. That's why first you will open the PDB, then you will open each Dcd onto that PDB file. Then I am adding the production too. So you will see there are 78 frames in the system, and you can see the water box in here. Let's get very bigger. So when you run this one, you will see the motion during the simulation in here, and we will actually observe this motion much more clear the next step. So firstly, I would like to continue with the creating new Dcd file. In this example, we are combining actually the two Dcd file, which one is first one is the accumulation and second one is the production. But for the R analysis and the Mda Analysis Python tool, we have to combine these Dcd data into one, and we will use this all Dcd file to analyze. That's why I am clicking to this input PDB. Then I am choosing save coordinates. Then in here I am firstly I will save the Dcd, and I am choosing the all. That means I am choosing the whole system, including iron, water, PDB, protein, and ligands also. Then I am saving it, and I am giving the name as all. This one is the without, so without ligands Dcd. The naming is important for your files either. You have to be careful about that. So now I am, now I would like to only save the protein as a Dcd. So that means I will separate the protein from the ligands, ions, and water. That's why I'm choosing only protein in here, and I click to save. And now in here, I am writing protein without ligands Dcd. And that's it. And also you can see here, first frame is 0, last frame is 77, and stride is one stride means step. That means you will actually save each frame one by one without any passing. Stride means that one, and you can actually increase it if you want. When you increase it, your data will be decreased as a volume. And in here, yeah, and now I continue with the PDB part. Now, firstly, I am choosing the all again, because if you want to open the old DCD that we just saved, you have to use the special actually PDB for that. You cannot open the protein PDB on PDB which is the which contains only the protein data. You cannot open with the whole system. This is the important part, and that's why you have to save them separately. So for the PDB, I am choosing the only one frame when I write in here 000, and then I am choosing the firstly, I am choosing the first frame as a data for the PDB file. So now I'm here. I would like to save with the name this one. So okay, then I would like to save the protein. Then where is our protein? In here. So okay, now I save it, but I would like to change something about that. It makes me confused maybe. So sorry for this typo. So okay, now let's continue. Oops. In here. So now I am changing the representation. This is line, and I would like to separate our protein from the water. That's why I'm writing in here the direct protein, and I press the enter. Then the all water box gone. Then I am changing the representation with new cartoon, and I am changing the color with color ID and the magenta, this one. So this is our protein, and when you click the display, you will see the motion inside the box, but it is, you can see it moves in different position. And that's not good, because when we are doing the Rmst calculation, it affects our result. That's why first we have to align it when we for the Rmst calculation, before the Rmst calculation. So now, and I would like to open to you this. Where is it? Yes. So firstly, I will start with the RMSD. Probably you learned what is the RMSD, root mean square deviation, and it is the using for the distance measurement between two atoms. And you can compare two structure by using the RMSD. You can compare the motion, or you can compare the shift by using the RMSD, and the RMSD gives us that information. You can calculate RMSD by choosing specific frame, or you can do this RMSD calculation by using reference, and reference can be generally actually it is the first frame. For this example, we are choosing the first frame as a reference, then we are aligning each frame to the first frame. Then we are calculating the distance between the atoms, each atoms. And you can see the example in here. And this is the reference structure. And this is the frame number, frame structure one by one. And we are doing this calculation. This is the summation. And now let's continue with the here. To do Rmst calculation in the DMD, you will go to the extensions, analysis, then you will see the Rmst trajectory tool. So in here, I am choosing the protein because I don't want to do anything about the water. Water actually is, the usage of the water is done here. And we used it in the MD simulation. Now we will analyze our protein only. That's why we are we remove the water. Then we continue with the protein to the next analysis. So I am choosing protein in here, and I am choosing the backbone either. Then I am choosing save, and also you have to change the direct path of the this file. So you can take it from in here, not in here. Let's open the new window. Then go to the desktop. Structure. Copy paste for the paths is the best way, because sometimes when you are write the paths by your own, then you can actually make a mistake. You might make a mistake, and that's not good. That changed everything about the result and etc. That's why I will continue with this part. I would like to get the paths for the working directory. So now I am working with the without ligands. Now TVD. So this is our path. I am choosing this one, then I am pasting in here. So when you click the save, your trajectory Rmst data will be automatically saved, and when you click the plot, we will see the plot directly in here, given from the DMD. So firstly, I am clicking the align. I have to do align it. Then you will see the motion right now. It is different. The protein is stable, not moving around. So you can see that's why we will do this Rmst calculation right now. It is the how to way actually. Then you will click the Rmst, and this is our Rmst graph. So in here, the x-axis means the frame, and the y-axis means the Rmst result value. And you can see the differences between the frames, and the reference frame is the first frame. And in here, you can change, select the reference molecule, top, average, selected, etc. And generally, we are choosing the first frame. Now, for the last frames, you can see our structure getting much more, actually not shifting, it is getting much more dynamic. This is the idea when we are looking at the Rmst. Rmst gives us that information. And also, if you want to draw the plot, you can use this Traj Rmst data, and you can plot it by using the Python or another tool. And that's it for the Rmst part. Now, in here, we will continue with the Pca analysis. Before that, I would like to show what is the Pca analysis. In here, Principal component analysis is a standard mathematical tool used to detect correlation in large data sets. If you have very large data, and if you have very different type of data inside your data collection, then you have to decrease your variable to get the actually meaningful information from the data. That's why we are using the principal component analysis. It gives us the important information from the data, and we can understand for the actually MD simulation, we use this principal component analysis to get much dominant conformation inside the simulation. So in the simulation, we saw a lot of conformation, and some conformations are repeated, and some of them are the dominant, and we would like to see the dominant conformation throughout the analysis. That's why we are using the principal component analysis. So and we will get to this cross correlation map, and this is coming from the R, and I will explain it later. So in here we will get this figure from the VMD. Firstly, to calculate the PCA, we need the normal mode wizard tool, and you can, so you can download your ProDy. Firstly, you have to have the normal mode wizard, then you have to install the ProDy, and it is the tool for the VMD, and you can directly install it by using these codes, or you can download this tar file, and then you can open and build it and install it. So and also you can find the, where is it, needed information in the GitHub. In here you can see the tutorial in here. So I click the extension, and then I am choosing analysis and normal mode wizard. When I click normal mode wizard, it will, and also my VMD is not working very well, sorry about that. Then I will click the ProDy interface. Now in here I am choosing my molecule, which is the step 3 input. And then I am choosing the selection for the PCA. Generally, we are using the carbon alpha atoms, because PCA analysis is done by using the matrices, eigenvalues, and eigenvectors. And these eigenvectors, eigenvalues are huge. That's why we have to minimize our data to get the meaningful information. That is why we are using generally C alpha atoms for the whole protein. But if you want to analyze a specific region inside the protein, and this region is if this region is very small, then you can use the whole atom inside that region. But normally you have to pay attention to the actually your data. If it is too huge, or if it is too big, then you cannot calculate your PCA, because probably computer will crash. And that's why in here I am choosing the only protein and name C alpha. I am choosing first the protein, then I am choosing the carbon alpha of the protein. Then I click the select, and in here I am choosing the path to save it, and oops. So, and without applicants. Yes. Then I will choose the PCA calculation in here, and also you can do ANM and GNM calculation either, but they are a little bit advanced for us right now. Then I am clicking the remote coordinate open job computation. There will be a lot of file when we are calculating the PCA. That's why I would like to remove this coordinate file when the calculation is done. Then you can write your cross-correlation heat map in here and load in here. When you click this one, you will see the file on the your directory. Then I am choosing the mod number. Normally, generally, we used actually, I used actually 3 mods, because the other mods are not meaningful as much as the first and the first 3 actually. that's why I'm choosing the first 3 modes. Then I am doing alignment. I did alignment, but if you don't, you can click in here, because when you don't do the alignment, then you will get a probably wrong result. That's why alignment is important too. And our trajectory type DCD. Then I am clicking the submit job. Yes. Oops. Without to invest. Oops, sorry. As I said before, my VMD is not working very well, and probably that's very nice. Normally it is working, but right now it is not working, and I don't understand. If to do that, I will open it again. In the Mac, VMD is not working correctly, and normally VMD is very tough program to run it. That's why it does say the PyMol is a little bit easy than the VMD, and Gmail says that. So now in here, I will continue with the directly this one, for example, right now, because we actually, so, and you will see 79, because our DCD file contains 78 frames and our PDB file contains 71, and the first frame is in here for 2 times. So then I am going to go to normal wizard, ProDie interface, name C alpha, select it, PCA, and not here. So I hope it will work again. Yes, we would like to specify our ProDie path, but probably I erased it. And where is it? ProDie. And where is Dolan's? Yeah, in here, ProDie in here. So I am going to go to the ProDie. I lost. So user, not local, where we are, users. In here, sorry. So yes, Dolan's. This way. Oh, come on. In here, we are guests. That's why. Now I am going to Savos. Oh, sorry, guys. Desktop, ProDie, open, which is the, probably this one. Oh, sorry about that. I will show it in here. It was worked last night, but it is not right now, and I don't like that one. So when you open the when you run it, you will see this image. So this image represents the motion, the dominant motion inside the trajectory, and that means when you run it, you will see the motion in here like that, and each arrow represents the motion direction, and also you will see in here blue, red, and white color. That means the blue ones are moving much larger, much more than the other parts. And also you will see when you run it, the one chain will be stay in here, and then other one will be moving. And that means the reference chain will be stay, then the other, your PCA result, which is the model 1, will move. And for the PCA, you will actually get this information for the BMD. Now, I would like to continue with the BMD makes me sad. So I continue with the weak ligand structure. So in here, weak ligands, not this one, this is the test. So weak ligands, I am uploading the step 3 input, then I'm uploading the equation and this one. So now you will see there are 78 frames in here too. Then again, not a molecule, sorry. Then I click this one, then I am save coordinates. I save coordinates. Firstly, I am starting from the DCD and ligands. Yes, all with ligands and protein. And I will continue with the PDB. And okay, now I am again clicking to this one. I am choosing the protein. I'm changing the representation to see the differences much better. Then I am changing the color with sign. This one, then you can see. Now, and also I would like to show this one too. When you go trajectory, it represents the now. That means when you go there, it will represent the 59th frame. If you write in here 0, 5, you will see this representation. That means you are actually in here. You see the each 5 frame up to 78. And if you want, you can increase this one, and also you can change the color ID with the not beta trajectory time step, and you will see. And it is not good because we didn't align it yet. So I am going to go to Rmst trajectory. I'm choosing protein, backbone, plot, save, align. Then you will see. these are the actually which one? Each 10th frame in the simulation, and we put them to each other, and that's why we are seeing this one like here. And also, if you want, you can see all of them. See? So let's go to the novel, and I am changing to again color ID side 2. So now in here again with ligands, then top backbone, plot, save, align, RMSD, then you will see the result in here either. And I will show the differences between these RMSD plots in the R. It is a little bit understandable more than this one. So let's try again ProDive, but I'm not sure it will work. Probably not. But I would like to try it anyway. So let's write in here. Remove, right, submit job, and again. Yes, let's continue. I'm so sorry about that one. I did 1,000 times demo for you, but it is not working well. So now I am continuing with the R, and you can download R, then we will continue with the Bio3D, and you can find the installation and the installation link in here for R and R Studio. Then we will work on with the Bio3D, and this is the library for the R, and it is very useful library to analyze the trajectory and also do some calculation. And today we will use only the trajectory analysis in here. Not this one, this one. When you go there, you will see beginning trajectory analysis. We will continue with this one. So in here, also this tutorial is very nice. I will continue with PCA, that's why I'm showing that one. Yeah. Okay, I will show this multiple frames at the end of the this session, okay? I am sending the GitHub link to you. You can find each link in here. So now let's continue with the R. Now, if you have R Studio already, then you have to, in here, you have to you have to download the Bio3D. So installing Bio3D. You will write directly install Bio3D, install packages period Bio3D. You don't need to write this one. So when you write this one in here, I already downloaded it. But when you click this one, it is very fast to download it. So yeah, we have already. Then now I have to call that one. Now I am writing in here Bio3D. Then I call it. Now, sorry. Yes. Now I am continuing with the reading PDB. In this R, you have to firstly go to the, you will see your path in here. If you want to change your path, starting path, you will click the RStudio, then you will click preferences, then you will change your working directory for the each opening. So I choose this test one, that's why it is in here. So let's continue, and I would like to show this is the terminal. Actually it is the same with the first one. So I am here, 3D, then I would like to go to these files, and let's continue with the weekend. So now I am getting this path because we call our PDB file from this path. That's why we need this path. You can go take your path in here. Then I am writing in here PDB. PDB means our variable. If you want to assign something to, if you want to assign a variable, and if you want to assign a value to a variable, you can use this sign. And then now I will read my PDB. This is the function for the Bio3D library. Then I am writing my path in here, and I am writing directly to protein. Protein with, I think, PDB. So you will see PDB in here. When you click this one, you will see the information, XYZ, C alpha, language, atom. You will see the atom information, etc. So now let's print our PDB. And you will see information either in here, protein sequence in here, protein atom numbers, total atoms, XYZ number, coordinate number, and C alpha atoms in here. So this is the summary for your PDB. And now if you want to get the information about the coordinates, you can write XYZ in here, and you will see the XYZ result in here. This number is the actually coming from this one. When you multiply this number with the 3, that means the coordinates XYZ, then you will get this number, and it represents the coordinates of each atom, and it is the list of that. So now let's load our Dcd file. To load our Dcd file, again, you will call the read Dcd. It is very easy. And then I will call my Dcd file for this one. So Dcd. Don't worry about these warnings, it is not error. In here you will see atom number, frame number, last and step and file version. So when you click this one, and you will see again, oh, this is a little bit long. When you click this one, you will see a lot of number in here. There are 78 rows, that means the frame number, and the coordinates are written in here too. It is a little bit big. So if you want to see the information about your Dcd, in here you can write directly Dcd, and you will see XYZ coordinates in here too. And this is the matrix dimension. And when you click this Dcd, you will see this matrix. So now I would like to get the C alpha indices. So to do that, I am writing this. This is our variable name for the C alpha indices. Now I am selecting my atoms. Atom select. I am selecting from the PDB. Then oops, equal to C alpha. You can select your carbon alpha atoms by using atom select, and you are defining your variable, which is PDB, and we are defining the atom type, and we are assigning this result to the C alpha indices. So now let's see your C alpha in here. Then let's continue. Now I would like to get the coordinates of that C alpha. So in here I am writing XYZ because we will do the actually some calculation based on the C alpha atoms. That's why we need the coordinates of the C alpha atoms. So I am assigning XYZ as a variable name. Then I am writing in here fit XYZ. You can find each comment from the tutorial on the tutorial. So now I am writing in here fixed equal to PDB XYZ. We are assigning to this one. Then mobile are motions are inside the DCD. That's why we are assigning the mobile equal to DCD. Then fixed indexes, indices, not in, yes. And we are assigning this one the C alpha indices XYZ. Then we need the mobile indices either. So I am here indices, and this will be the C alpha indices again XYZ. So yes, because this will be the $sign. Okay, so let's compare. Now we got the XYZ coordinates of the C alpha atoms. So I would like to check these coordinates are the same with the DCD coordinates. To do that, not the actually same coordinates. I would like to check the dimension of them. That's why I am writing in here XYZ equal to dimension of DCD, because this dimension should be the same for both XYZ and DCD, because we are only take the C alpha carbon alpha atoms coordinates, and the number of the carbon alpha atoms are the same with the residue number, and that's why dimension number should be the same. And you will see this is equal to each other. Now, I would like to calculate the Rmst in here. So I'm assigning this Rmst to Rb. Then you can directly call your function as a Rmst to calculate Rmst. Then I am choosing the XYZ. This is our variable that contains the coordinates of our structure. Then I am choosing in here 1 to C alpha indices XYZ. And again, XYZ. Alpha indices XYZ. So now I calculate the Rmst in here. I choose the first frame C alpha indices as a reference, and then I am choosing every frame after the one by one with the coordinates of them, and I calculate the Rmst between each other, and assign the result to RD. So when you click the RD, you will see again a matrix, and it is very huge. That's why it cannot open it. It is valued. That's why we cannot open it with the data in here. So if you want to see this Rmst result, we can observe it by using the plot. We can do the plot based on the Rmst. So I am writing in here type, that means line, and line should be inside the quotation. Then Y lab will be the RMST. This is the Y label RMST, and X label will be equal to frame no. So when you click this one, you will see the result in here, and you will remember it. This is the same with the VMD results, and the RMST results are the same, and because the formula is the same. So that means we got the true results. When we look at in here, I can say that when I go to the last frames, I see the actually protein getting much more dynamic, and now we can continue with the and also we can determine the average of this RMST. This is the line, but if you want to represent the average of it, points lowest RD, then again type will be equal to L, then color will be equal to red, and equal to, this is the width, I think. No, this is the width, this is the length. So equal to 2. And I forgot something in here. Color red, LRD points, histogram. What should I forget? What? 2, L, type L. What was, okay, RD. Put the coordinates, RXT should be coordinated. Sorry, it should be LVD, but it is not working. Yeah, it's working, sorry. This is the warning. So you can see this is the average line for the RMST. You can calculate RMST. And in here we are assigning color. In here we are assigning the type of the graph, which is line. And we are taking the RMST result as a input. Then we are giving the length of the this line, and this is the width of the line. So now we can see this RMST by using the histogram. And what is the time? Okay, so we can create histogram by using this one, histogram, and RD, this is our input data, and we are determining the breaks as a 40. This is the actually default for the tutorial. So I am ignoring the frequency. Then main will be equal to RMST histogram. That means the title X lab will be equal to RMST, and that's it. See, this is our histogram. This is the blocks breaks, and this is the frequency. We ignore it. Main means the title, and the label of the X is the RMST, and we can see the distribution of the RMST in here. If we want, we can show this distribution by using the line. So to do that, we can call the lines density RD, call gray, color gray, and line width will be the 3. And you can see this is the line distribution for the RMST results. So when I write in here summary RD, and I will see the median, mean, third quantity max results for the Rmst data in here. So, and also minimum it's in here. And this is 0 because we are choosing the first frame as a reference, and then we are starting to calculate. We are using we are starting to use each frame to do calculation one by one by comparing the reference, and the first frame will be the 1 and the reference frame will be the first frame. That's why the Rmst, minimum Rmst will be the 0. That is the reason. Then now I would like to see the fluctuation inside the protein while simulation, throughout the simulation. To do that, we can do Rmst Graph fluctuation, RMSF. And RMSF is a calculation of individual residues flexibility, or how much a particular residue moves during a simulation. And we will see this result. And it is this is the formula of it. And again, we will choose the reference. Then we will compare this reference one by one with the frames, and we will find the thanks to this equation, we will find the fluctuation inside the frames, throughout the frames. So to do that, again, I am assigning the variable results RF, RMSF results to the RF. Then I am calling the RMSF function. Then I am taking the, not this one, sorry, it should be this one. So I'm choosing the XYZ coordinates, and I'm choosing the whole frames. That's why I'm not writing any number before the comma. And then I am choosing the indices and XYZ, not item, XYZ. So I create the RMSF data. Then I will plot it again. Plot. Our input data will be RF. Then I will, it will be the same actually with the, where is it? This one. So that's why I'm copying it in here. This will be the RMSF residue position, not RMSF. And X label will be this one. And this will be the type equal to, okay, that's it. See, this is the RMSD, RMSF. That means the fluctuation information for the R simulation. This we are doing this analysis for the with ligand structure. That's why this is the difference from the in the slides. This is for the without, that means the upper one, and you can see the differences when we are adduct ligand to the R protein, and it's let's see in like that. Yeah, you can see the differences. R structure is changed when we add the ligand. So now I would like to calculate the PC. PC means principal components. Pca analysis contains principal component results. Principal component means the modes, and each mode represents the conformation inside the trajectory, inside the simulation, and the first PC represents the dominant one. That's why we are doing the PCA again. I am explaining it again. So now I am calculating, I am gonna calculate the PCA, and I am calling the PCA XYZ. Then I am choosing the, again, coordinates, which will be the, again, whole frame and C alpha indices, XYZ. I calculate the PC, and you can see this is a large PC. You can see the mean in here for each one, standard deviation, And you can see also each feature on the tutorial, explanation of each feature on the tutorial. So now I would like to plot it again. Plot PC. And all will be the colors. Then XYZ. See, this is each dot represent the frames, and you will see the distribution of the frames for the PC1 and PC2. When we are comparing these frames for the PC1, you will see the distribution in here, and first frame is starting from the blue, then to the last frame will be the red, and the color is actually determined between these two colors. And then you will see the eigenvalue in here. For this graph, we can determine the R cluster number. Now we saw the distribution of that, and now I would like to cluster of them. For example, I would like to cluster as a 2 for these frames based on the conformation, for example. But in here, for the healthy calculation, you can choose your cluster number by looking at this graph. And when you look to this corner, it will say to you the cluster number. The cluster number will be the choose by looking at this corner actually, and this is the proportion of variance. This is the variance. This is the eigenvalue rank, and this corner gives us the possible cluster number. So now in here, I am creating this one, and I will explain it a little bit later. Now in here, I am calculating the cluster list. Now I will do this cluster based on the PC principal component results, and I'm choosing the Z. And again, all frames and 1, 2. This is a little bit advanced for you, and I did something wrong. Which one? Cluster this PC, this one. This should be the normal. Okay. Again. So now I have to plot it to see, and then I have to group it. I do the cluster calculation, then I have to group it. So I am creating the groups. Then cut 3, and I'm writing my input data. Then will be 2. So our cluster number will be 2. Then I will do the plot of it. So plot. Firstly, I will use the PC with call equal to groups. I'm calling the PC, but I am color it based on the groups. So you can see we separate our frames into 2 groups. And in here, I am calling my PC results, and I am color it based on the groups. And we create these groups based on the cluster. We got the data to do clustering, and in here we are doing clustering based on the 2 cluster, and we are seeing the result in here. And this is the 1 cluster, this is the 2 cluster, and we are seeing the distribution between the PC1, PC2. That means the mode 1, mode 2. So now what else? Let's do this one either. So now I would like to do this plot view 3D, PC. This is a little bit long. Sorry about that. Now, one YLab, PC1. Okay. Label will be equal to residue position. Type will be equal to out. So you can see the distribution of the residue position for the PC1. So in here, you can see the residue position inside the model 1. It gives that information. It gives us that information. So let's do point. So then I would like to do this results. So and color will be the blue. Now I am creating the color blue. Type out. I did something wrong again. Points. I forgot this. So in here, the actually blue one represents the PC 2. We are combine PC1 and PC2 result in here. The black one represents the PC1 and the blue one represents the PC2. We can compare with first two dominant structure with each other. Then, and this is the last part. Now I would like to see, I would like to get this cross correlation. This cross correlation map represents the actually conformation result. How can I say? That means when we are in here, going to here, that means our residues are getting closer. And when we are going in here, that means they are negative correlation. They are getting away from each other. And when we are go here, that means they are getting closer, closer to each other. That means the positive correlation in here. So I will calculate this one. To do that, I will, oh, okay, not this one. So CI PCA equal to DCCM, not equal to, sorry. DCCM is another function to do this calculation, cross correlation calculation. And I would like to do this cross correlation calculation based on the PCA. That's why I'm writing in here PC. And in here, I am assigning this PC 1, 2, 3, 1, 3, sorry. So now I will plot it, plot CIG PCA, and in here I am determining the color of the graph. So in here I am determining the column regions with this code colors 20. This is the you can think like this is the default code, and sec equal to -1, 1, 0. Sorry, 1, 1. Oops. Color region, bright colors. Color regions, bright colors. Again, many arguments. Why? Because it should be this one. So pay attention to each dot. It takes time. See, this is not good result. So the correlation is very small for this result with the ligand one. Normally, we generally see it like this, and that means there are some negative correlations in the blue one, and there are some positive correlation. That means they are getting closer to each other for the red ones. But in here, this is not good result for our ligand structure, and also for this 3LZV, I think this protein is not enough to small simulation, small time step simulation. That's why we are not catching meaningful results from the simulation. We choose the very small structure to do this simulation in a short time. But after the simulation, we got the result, then these results are not much meaningful. That's why we are seeing this result in here. So this is it for the R part. Now I would like to show to the Mda analysis to you. Yes. You're welcome. So in here, I will use the Colab. Maybe you know that, maybe you don't know. This is the online tool, and this is the Python prompt, and you can do Python analysis on this Colab. You have to have the Gmail account to use this Colab. When you write Google Colab, you will see the this Colab as a result at the first part, and then when you click, you will see. Then you will click the file. Let's see. Let's do it together. If you don't know, right in here, Colab, not this one. Sorry, my computer is getting slower. So you will see this one. So when you click the file, you will see the new notebook. When you click this one, the new page will be open, and you can start to type it. So in here, I will explain the code directly because I don't want to lose time. To use the Mda analysis, firstly, you can find the information about the Mda analysis from the GitHub. I explained, I give the each link about the Mda analysis. This is a good tool to analyze your trajectory results and analyze your Mda simulation results. It is written with the Python, and it is the Python tool. And to run it, you have to have the NumPy, and also you have to install it, and the installation is very quick. So if you want to install it by using pipe, you can write only these two, only this have to call it to use it. Now in here, I am calling my Mda Analysis. If you don't know anything about the Python, I would like to explain in a short. So if you would like to call the Mda Analysis, you have to import it. Then you are giving a new name, like a variable name, to use it actually efficiently. So I assign this Mda Analysis as a MDA. Then in here, you have to click this folder. Then you will click this upload button. Then you will choose your data in here. And I choose this PDV and DCD as a result in here. Then you will upload it as a universe. That means you are combining PDV and DCD like in the VMD. Then you can determine, you can check your version. Then you can assign your PDV to PDV, DCD, DCD, and you can check your trajectory information for the PDV. In here, you can check your DCD. You can check your length of the DCD trajectory, which means 78. Then I would like to run it, but it takes a little bit time. So probably we, oops, let's do it with, what did I use? Without ligand. So I am uploading the without ligand in here. Not PCA, DCD. So these steps are very fast. That's why if you want, you can do it right now with me. So I'm uploading the data in here too. And actually, this is not necessary. I'm upgrading my Mda Analysis. So let's continue. In here, I am assigning this universe as a U. And you can check the information about the universe. That means the structure system that contains PDV and DCD. And you can check information for the trajectory, length, residue atoms. And in here, yeah, it's done. And let's import the matplotlib. So we upload the file. So now let's run it. So you will see the result in here. In here, print PDB. You can see the PDB atoms in here, atoms for the PDB and trajectory length, which is the 78. And you can check this trajectory length by using the universe again. And in here, you can calculate radius of gyration. And I would like to show it what is it in here. Radius of gyration is the Rmst of the atoms from the center of density in the molecule weight. You are calculating the Rmst based on the center of the whole structure. And this center is determined based on the density. That's why you are, for the first part, we calculate this Rmst based on the each frame. We take the first frame as a reference. In here, we are taking the center of density as a reference, and we are calculating the Rmst by using this center of density reference with each atom. And normally we will get this type of results, but we are getting a very different result from the Mda Analysis. But just I would like to show it to you because our selection is not good for as a protein. That's why our result is not very meaningful. So in here, we took the first 20 frame, then we take the time from the trajectory, and then we calculate the radius of gyration, and we are printing it one by one. You can see first 20 frame radius of gyration result in here. And in here, we are taking the trajectory frame as a frame, then time. Then we are calculating radius of gyration again, and we are writing this result, which is directly this one. And this is for the first frame, because when we write this one frame, u trajectory frame, that means you are getting the frame for that now, and this frame will be the 0 for that now. I don't know how I can explain it, but for the first time you are choosing the first frame as a for the calculation, and that's why when you are writing trajectory frame, you are getting this frame as a reference to this frame variable. So that's why when you do that, you will see the same result with the frame 0. So in here, we would like to actually plot the radius of gyration versus time. And in here, firstly, we would like to choose the protein, and then we are creating the time array and radius of gyration array, because in here we are calculating a radius of gyration for each frame. Then we are putting each result to the array, and then we will plot it. In here, we are calling the pandas. Pandas is another library. And now in here, we are getting the data frame from our data. That means we are getting directly this radius of gyration part from our data. This is our data. That's why we are getting this one. Then we are determine the time as a femtosecond, and then we are seeing the radius of gyration head in here again. This one. This is the first one. So it is a little bit complicated. Let's test it. Then I am plotting it for each time step. Femtosecond, that means, and this is the radius of gyration result, and we can see the distribution of each atom based on the center of density. This is the result for the radius of gyration. In here, you can do Aromastic calculation. Let's do it by using the RMS function from the Mda Analysis library. Then we are assigning the backbone. We are choosing the backbone atoms as a BB. Then we are getting the first frame. Then we are getting the position of the backbone inside the first frame as a first, and we are getting the last frame, and we are getting the position of the backbone as from the last frame as a last. Then we are comparing the first frame and last frame, and this is the RMST result between the first and last frames. And in here, we are selecting backbone, named C alpha, and protein. We will do the RMST calculation for both three of them. Then this is the R function. We are selecting backbone, and they are the other group selections. Then we are running our RMST. Then we are printing the shape. In here, you can see the results. Then in here, we are actually choosing again our data as by using the data frame, backbone, C alpha, protein from the results, because the result will give a lot of information, about the RMST, but we would like to get only the value of the RMST. That's why we are choosing the data frame in here. And also we are choosing the time as a x-axis. That's why we are choosing the time PS index name. Then we are plotting it in here. This is the head, this one. This is not necessary. Now we plot the RMSD based on the backbone, C alpha and protein. And you can see C alpha and backbone are the same. Generally, if we want to calculate the backbone by using the RMSD, if we want to calculate the RMSD by using the backbone, generally we choose the C alpha atoms. And that's why the results are the same for both each other, for both two of them. And this is the protein, and they are different because the atom number is not the same with this two structure. Protein contains a lot of atom than the C alpha atom. That's why the result is different. And in here, you can do the RMSF calculation either, but this is not good result because of our selection as a structure. So this is the example code, and I will upload this code to GitHub, and you can do this analysis by your own. And that's it for the MD analysis. So I would like to show last things. I know our time is up, but if our VMD is work well, I would like to show the how to. You're welcome. So I would like to compare not bonds between the ligand and the protein. So I am going to with ligands, and I am choosing the all, not this one, sorry. First PDB. And oops. Why? Sorry. Let's start from the beginning. Oh. Rows. PDB. Open it. This should be PDB. Where is the PDB? Here. Load. Then I am loading this one. So in here you will see, let's change the representation. I am creating the replica. For the first one, I am choosing the protein. And for the second one, I am choosing the ligands. If you don't know the ligand name, you can go to the seg name. This is the segment name. And you will see HETA in here. HETA is our ligand name for this system. And now I am choosing our ligands with this keyword. So now let's change the representation. This should be this one, and the protein will be the new cartoon. So you can see in here, this is our ligand and this is our protein. And now I would like to do some calculation, bond calculation. So in here, let me check my notes. I choose HA1. Yes. So to choose an atom, you will press the 2, and then also please create a replica in here too, because I will calculate the bond between the residue 49, and I am choosing this one. I am changing the color to see properly, and I'm choosing red in here. So in here, I am choosing this. I would like to choose this atom, so I click this one. So then I will click this one. I hope it will work, but I don't know. This is not good. Oops. You can see your label bonds with the graphics labels. And I would like to do this selection again, and I would like to do this bond selection again. So I choose this one. So for example, this is not good one again. PMD is doesn't understand me today. So let's choose this one. Yeah, yes, let's check this one, for example. This is the bond between the glycine 51 and ligand cysteine atom. So in here 51, that's why I am choosing the in here 51 to see properly our residue, this one. So I would like to see the changes in the bond during the trajectory simulation. During the simulation, I would like to see changes inside the bond, changes of the bond during the whole simulation. That's why I will go graph and show preview, and then I click the graph. Before that, I have to choose this one. Then I click this one. You will see the bond changes during the frames. This x-axis represents the frame, and this is the value for the bond. And you can see for example, at the end of the frame, and at the end of the simulation, this bond is getting very larger than the first one, for example. You can say like that. And you can see the differences in here. This is the peak. This is the minimum. So yes, when you click this save, you can download the data, graph data directly. So let's continue with your question again. Draw multiple frames. So I am showing these multiple frames to you again, and this will be the last things for our session. Again, I am tracing bonds and atoms one by one. So now let's close this one and close this one. So we are seeing only this one. So now I would like to see the whole trajectory distribution on this structure. So now that's why you have to write the first frame number, then the not step number, let's say. We would like to see each frame in each 5 steps. Then I would like to do this calculation, do this action up to 78, which is the last frame. When I click enter, you will see the result. And if you would like to see the distribution based on the time step as a color, you will see this one. But sorry, so but this is not aligned. That's why this is very complicated. That's why if you would like to see much clearer, you have to align it with each other. So see, this is much meaningful, much more meaningful. Okay, do you have another question? So thank you for today. This workshop is very important for us, and we are happy to see here. It's happy to see you in here, and we would like to do something. We would like to do such workshops in the future either, and I hope you enjoy it. And if you don't have any question, I will actually give the words to Batuhan.
There was one request in the chat box. I don't know if you have seen that, but they ask, can we save raw data for this graph?
Yeah, I explain it. If you click the save button near the graph, it will automatically save.
And let me also check if there is any question in YouTube as well.
Mm-hmm.
It seems like there is no question in YouTube. Thank you very much. We have one more question. Can we contact you on email or on Slack channel if there's any problem?
Yes, of course, you can write me from the Slack.
Yeah, and if you're not in our Slack channel, you can register to RSG-Türkiye from our main website. Mm-hmm. And you can join our group. Yes.
Thank you for your explanation. Thank you, Batuhan.
Thank you for your very nice explanation and hands-on session. And we can end this session now. According to our schedule, we plan to have virtual party and networking session, but unfortunately, due to some unexpected health problems of some of our expected participants, we need to cancel this session. And if you would like to have such networking session in the future, you can write it into the feedback form. And if there is any request about the networking session, we can plan a networking session in the future. And now I will share the feedback form from the chat box. I'm sharing right now. Yes, I just shared the feedback form of this day, today's sessions. We would appreciate if you could fill this feedback form to improve our next events. And yes, there is a request about adding you the mailing lists. Yeah, we add our new members to our mailing lists as well. So you will definitely be notified if we would organize any new events. This means that we came to the end of this weekend's workshop. I hope you enjoyed, and I hope it became beneficial for you. And we hope we could teach you some basics of the structural biology. And we're planning to organize some other workshops and other different kinds of events in the future. And stay tuned, and you can follow us in our social media accounts, and you can register us from our main website. So this is the end of our workshop. Thank you very much for attending, for your participation, and see you in the next events. Take care. Goodbye.